In this video, we'll look at another question from our worksheet on Newton's law of gravitation or satellite orbits, right? So our worksheet on Newton's law of gravitation, satellite orbits. Now, this time we look at a question which says that a man is able to jump vertically 1.5 meters on Earth. So a man is able to jump vertically 1.5 meters on Earth. What height might he be expected to jump on a planet of which the density is 1/3 that of the Earth, but of which the radius is 1/2 that of the Earth? So once again, a man is able to jump vertically 1.5 meters on Earth. What height might he be expected to jump on a planet of which the density is 1/3 that of the Earth, but of which the radius is 1/2 that of the Earth? So once again, we'll begin by writing down the information that we're given, right? So we're told that this man could jump a certain vertical height on the Earth, and we're going to call that height HE, right? So the height that he can jump on the Earth, HE, equals 1.5 meters, right? That is what we're given. Now, basically, we want to find the height he would be expected to jump on a planet whose density is 1/3 that of the Earth's. So if we use the subscript E for the Earth and the subscript P for the planet, we will see that the density of the planet, rho subscript P, we're told is a third of that of the Earth. So this is equal to 1/3 rho E. We can actually switch this around a little bit. So the density of the planet is equal to a third the density of the Earth, or we can say that the density of the planet over the density of Earth is equal to a third. Or we can even say that, if we can flip it around, we can therefore say that the density of the Earth divided by the density of the planet is equal to 3. So we're dealing with a ratio here. And because we're told that the density of the planet is equal to a third the density of the Earth, we can actually express that in a few other ways. So we can express it in terms of the ratio of the planet's density to the density of the Earth, or we can also express it in terms of the ratio of the Earth's density to the planet's density, right? So throughout our look at this question, one of these ratios, of course, will be used. Now, we're also given a relationship between the radius of the planet and the radius of Earth. And we're told that the radius of the planet is 1/2 that of the Earth. So this would mean that if we call the radius of the planet r subscript P, then this would be equal to 1/2 times the radius of the Earth, from which we can also see that Rp over Re is equal to 1/2, or we can say that the radius of the Earth divided by the radius of the planet is equal to 2, right? So somewhere in our working out, one of those ratios, of course, will be used. Now, what directly affects the height through which one can jump vertically on a planet? We will have to say that is going to be affected by the planet's gravity or the planet's gravitational field strength at the surface, right? So the height to which a person can jump vertically on any given planet, of course, is dependent on the planet's acceleration due to gravity or the planet's gravitational field strength. Now, if we have a planet of mass m and let's say radius r, let's say radius r, yes, r. So radius r, planet of mass m, radius r. Then the gravitational field strength of that planet, of course, will be given by G is equal to Gm over r squared. So the gravitational field strength G of the particular planet will be given by Gm over r squared, right? Now, let's say, for instance, let the gravitational field strength of the Earth be Ge. So the gravitational field strength of the Earth, Ge, can be given in terms of its mass m and its radius r. So using our subscript from above, E for Earth and P for planet, we can say that Ge would be equal to Gm subscript E over Re squared. So the gravitational field strength of the Earth can be expressed in terms of its mass and its radius as well. So likewise, for the planet P, we will see that its gravitational field strength Gp would be equal to g m subscript p over the radius rp squared. And what we really want to get is a ratio for the planet's gravitational field strengths. And then that will basically then allow us to actually determine the height to which the man can jump, right? So what we can do now is, if we were to divide these two equations, we want to get the ratio of GP to GE. So we can say that GP divided by GE, this would be equal to GMP over R squared divided by, let me just put a stroke, divided by GME over RE squared. So this is RP squared. GME over RE squared. And of course, you know that when dividing by fractions, we invert the second fraction and then change the sign from division to multiplication. So therefore, this would give us GMP over RP squared times RE squared divided by GME. The G's will cancel, and so what we get is this, GP over GE. So we have MP at the top, ME at the bottom. We can put the ratios of the masses together. So this will give us mass MP over mass ME, and this of course would be times the ratio of the radiuses, or the radii rather. Then this would be RE over RP squared. Good? So basically we obtain an expression for the ratio of the gravitational field strengths of the two planets. And we can actually simplify it somewhat because we already have a value for the ratio of the radii. Sorry, the value of the radii of the two planets, right? Singular radius, plural radii. So the radius or the ratio RE over RP is equal to 2, right? So therefore this means that GP over GE is equal to, this will be 2, so 2 squared, that gives us 4, so this will be equal to 4 MP over ME. So therefore now, in order to find the ratio of the gravitational field strength of the respective planets, what we really need to find is the ratio of their respective masses, right? And that is what we will proceed to find. Now, we of course will assume that these masses are perfect spheres, and therefore we can actually find an expression for their volumes and therefore find an equivalent expression for their masses. So what we know is this. We know that density is equal to mass divided by volume, and therefore this means that the mass is equal to the density times the volume, right? So once again, we will obtain expressions for the mass of planet P and also for the mass of the Earth, and we will then find the ratio, right? So let's look at the mass of the planet P. So the mass of planet P would be equal to its density, right? Density, of course, would be rho P. So this is rho P times its volume. So remember, we said that the planets are perfect spheres, and therefore the volume of a sphere is 4/3 pi r cubed. So therefore the volume of this planet would be 4/3 pi times rp cubed, right? So that's basically what that gives us. So if we take out the constant outside, then this basically becomes 4/3 pi rho p rp cubed. And that's the expression for the mass of the planet P. We can do something similar for the mass of Earth, and so therefore this would mean that the mass of Earth would be equal to 4/3 pi, the density of Earth, times the radius of Earth cubed, right? So remember, what we really want to find is the ratio MP over ME, and if we were to then divide these two equations, what we get is this. The ratio MP over ME would be equal to 4/3 pi rho E P rather, P at the top, rho P RP cubed, right? So 4/3 pi rho P RP cubed divided by 4/3 pi rho e re cubed. Now clearly, the 4/3 will cancel, the pi's will also cancel, and so what we're left with is that mp over me is equal to the ratio of their respective densities, so rho p over rho e, times the ratio of their respective radii or the respective radius, respective radii, whatever, cube, right? And by now, of course, we should have these ratios. So from before, we know that rho p over rho e is equal to 1/3, and we also know that rp over re is equal to 1/6. Sorry, equal to 1/2. And so therefore, this means that mp over me, oh, this is going to be a 1/2, yeah, a 1/2 cubed. So we get mp over me would be equal to rho p over rho e, which is equal to 1/3, times rho rp over re, which is equal to 1/2, and that is going to be cubed. So we have 1/3 times 1/2 cubed. 1/2 cubed, that gives us 1/8. 1/8 times 1/3, that gives us 1/24. So basically, without even knowing the masses, we are able to obtain the ratio of the masses mp to me. So therefore, this ratio mp over me is equal to 1/24. And having found that now, we can basically substitute it here and then find the ratio of their respective gravitational field strengths. And this will allow us to find the respective height to which the jumper is expected to jump on the new planet, right? So let's just take this off. So we can now say that GP over GE would be equal to 4 times 1/24, which is equal to 1/6. And therefore, what this basically means is that the gravitational field strength of the planet GP is equal to 1/6 the gravitational field strength of the Earth. And what exactly does this mean in terms of the height that the particular jumper will be able to jump? If you basically go from a planet to another planet whose gravity is only 1/6 that of the planet from which you're coming from, then this basically means that you'll be expected to jump 6 times as high, right? So if on Earth you're able to jump 1.5 meters, then this basically means that on that planet you will be able to jump 6 times as high. So therefore, this would mean that HP is equal to 6 times HE, and this gives us 6 times 1.5 meters, which is equal to 9 meters. So therefore, on this planet, where the gravity is only 1/6 that of the Earth's, and of course we arrive at that due to relationship given between the density and the radii of the two planets, we can see that this particular jumper will be able to jump a vertical height of 6 times that on the Earth. And if it's able to jump 1.5 meters on the Earth, then it should be able to jump to a height of 9 meters on this particular planet.